Recently, we've been thinking about solutions and their concentration. We learned the main unit that chemists use to measure concentration is molarity. In this lesson, we're going to learn about some other units to measure concentration. For example, we'll learn about percent by mass and parts per million, and also parts per billion. Because different solutions have different concentrations, and they can be really, really small or really, really big, we need a range of units to describe them. And that's just what we'll talk about in this lesson. So let's learn about some other units of concentration. So remember that solute is the thing being dissolved. So let's identify the solute in each of these solutions below. The first one is acetic acid and vinegar. And so it's just telling you that acetic acid is what's in the vinegar. So that's what's been dissolved. So acetic acid is going to be our solute. Chlorine is what's dissolved in the pool, and phosphorus is what's dissolved in our drinking water. Remember that the solvent is what's doing the dissolving, and it's usually water. So even in vinegar, even though you don't see the term water there, it turns out that the acetic acid is dissolved in water. And so the solvent is almost always water. Similarly, for the pool, it's quite obvious that it's water, and for the drinking water, also obvious it's water. When you put together the solute and the solvent, you get the solution. So remember that the solution is combining those two things. Now here's the thing, we could measure all of these different solutions with the concentration unit of molarity, but it wouldn't actually work so well for some of them. Let's take a look. For vinegar, we would get 0.8 molar acetic acid. So that's a pretty reasonable unit to use. What do I mean by reasonable? Well, take a look at chlorine and you'll get an idea. In the pool, chlorine isn't around in very large quantities. It's around at 0.00006 molar, really small concentration, and that means molarity is not the best unit to measure in. Phosphorus turns out to be around in our drinking water in even lower quantities. Its concentration is 0.000001 molar. Okay, it is not around in very high quantities at all, which is good. Phosphorus isn't good for our drinking water and our water system, and it's actually regulated. But what's a good way to measure all of these? Well, it turns out that some good ways to measure them would be percent by mass for vinegar, parts per million for the chlorine, and parts per billion for the phosphorus. So you can see that all of these are much more natural units to describe the concentration that don't require a bunch of extra zeros. So what we're going to do in the rest of the video is we're going to talk about the definition of each of these units of concentration, and we're going to get a good handle on that, and then we're going to practice doing some calculations. All right, first, what are the definitions? Okay, well, the definition of percent by mass is this. It tells us that the mass of solute divided by the mass of solution times, it turns out to be 100, so we have to multiply by 100, gives us percent by mass. This is actually just the standard way to calculate percent by mass. We have the part that we're interested in, and the part we're interested in is our solute. That's the thing that is around that we're interested in thinking about how much of it is around. And then we have the whole, which is our solution. Remember, when I add together solute and solvent, I get solution. So this is basically just saying the part over the whole. The whole is the solution, and the part is the solute. Okay, now one quick note here, those units have to match. So if I use kilograms for the top one, I got to use kilograms for the bottom. Pounds for the top, pounds for the bottom. It wouldn't make any sense to mix those units. I wouldn't be getting a good percent by mass. So we've got to make sure we always have the same units. Last note on percent by mass, the units I'm going to use here will be percent and then M over M. Turns out there are other percent by masses, which we won't talk about, like volume over volume or mass over volume. And this is just to tell people, hey, this is mass over mass. So that's why we use that M/M. Okay, what about parts per million? Parts per million looks really similar. It's the mass of the solute, that's the part, over the mass of the solution. Exactly the same there. The only difference is that we're going to multiply by a different number. Remember, percent by mass, we said, was sort of like parts per 100, and we multiplied by 100. Parts per million is going to be multiplied by a million. So we're going to put a 1 and 6 zeros there. Okay, so that's a million. Now, another way we might express 1 million is in scientific notation. And so you'll often see the formula written as 10 to the 6, which turns out to be a million in scientific notation. What abbreviation do we use? ppm. Okay, so parts per million is a way to measure small concentrations. It's still looking at the mass of the solute over the mass of solution. Last one, parts per billion. Parts per billion takes the mass of the solute and divides by the mass of solution. Looks really familiar. So you can see all three of these have this same general pattern. And then what are we going to multiply by? You guessed it, 1 billion. Now, a billion is 10 to the ninth. And the abbreviation we're going to use is ppb. And parts per billion is a nice unit to measure even smaller concentrations. So very often pollutants or toxins that are regulated are measured in the parts per billion level because we want almost none of them around. Okay, let's do some practice problems. Here we're asked, a bottle of bleach contains 3.5 kilograms of water and 1.5 kilograms of sodium hypochlorite. Turns out bleach is sodium hypochlorite, and that's the same thing we actually call chlorine in the pool. So chlorine in the pool secretly isn't just Cl, it's actually sodium hypochlorite. What is the concentration of sodium hypochlorite in percent by mass? Okay, so I've broken down our process into a few steps here. Step 1 is identify the solvent and solute. So we're going to underline the solute in green. And our solute is going to be the thing dissolved that we're interested in the concentration of. So that's the 1.5 kilograms of sodium hypochlorite. And the solvent is our water. Okay, great. And now we want to write down their masses. So we're going to write down the mass of our solvent, which we know is 3.5 kilograms. And we're going to write down the mass of our solute, that's the thing we're dissolving, which is 1.5 kilograms. All right, so now I've made good progress because I've identified what information I need to know and I've labeled it. That's great, and that's always a helpful thing to do. So we're through step 2, and step 3 is ensure they have the same unit. Remember, we said that the top and bottom have to have the same units. So in this case, all of our units are in kilograms, so we're good. Now we want to calculate the mass of solution. How do I do that? Remember that the solvent plus the solute is our mass of solution. So my mass of solution, which we've been using yellow for throughout this video, is going to be equal to my solute, which I know is 1.50 kilograms, plus my solvent, which I know is 3.50 kilograms. Awesome. That gives me a total mass of 5.00 kilograms. All right. Now we're going to go ahead and calculate the concentration that we're interested in. We're interested in percent by mass. So we'll write percent by mass equals the mass of my solute, which we know is 1.50, divided by the mass of my solution, which is 5.00 kilograms. And when I do that, I'm going to multiply that whole thing by 100, just like my formula says. And I'm going to get out 30.000 zeros forever for my percent by mass. Now, how many sig figs should I have? Well, if we noticed that each of those masses I've been given has 3 sig figs, so each of those masses has 3 sig figs, 1, 2, 3, then that means I need to round this guy to 3 sig figs, 1, 2, 3, and I'm just going to get 30.0%, and then I'm going to put m over m to make it clear that it's a mass percent. Okay, so that's a percent by mass problem. Let's take a look at a slightly different problem. Okay, here we're asked, a 100,000 gallon pool has a total mass of 385,000 kilograms and contains 3.8 pounds of sodium hypochlorite. What is the concentration of chlorine in parts per million? And remember, chlorine just is sodium hypochlorite, so those are the same thing. And so it's just asking about the concentration of sodium hypochlorite. In this case, we are going to start with our same steps, identify the solvent and solutes. Okay, so let's do that. So when we identify the solvents and solutes here, we'll see that there's a slight difference. So the solute, pretty straightforward. It's our chlorine, and we're going to underline that, 3.8 pounds of sodium hypochlorite. But where is our solvent listed? Notice this says total mass of 385,000 kilograms. Okay, so when it says total mass, that's actually telling me the mass of solution. Because it says total. All right, if it just said the mass of water, that would be giving me the mass of solvent. So you can see a really important part of these problems is identifying correctly your solute, solvent, and solution. Because it says total, that's our key, that's actually the whole mass of solution. Okay, so now we want to write down the masses that we have. And in this case, there's a slight difference here because we're already given the mass of solution. So I'm going to write down the mass of solute. And we know that the mass of solute is 3.80 pounds. And now I'm not going to write the mass of solvent is equal to 385,000 kilograms because that's the total mass. I'm going to write the mass of solution. equals 385,000 kilograms. Okay, now I'm going to go to step 3, which says that ensure they're in the same unit. Okay, well, they're not in the same unit. Notice this one's kilograms and that one's pounds. And so I'm going to need to use this conversion factor up here, which tells me that 2.2 pounds is equal to 1 kilogram. And what I'm going to do is I'm going to go ahead and take solute to kilograms. I could go the other way. I could take solution to pounds, and that would work just fine as well. So remember, I want to cancel out pounds and I want to go to kilograms. And so that means that my 1 is going to be up top and my 2.2 is on the bottom, just like I see up here in my conversion factor, 2.2 with the pounds and 1 with the kilogram. Okay, when I multiply 3.8 by 1 and then divide by 2.2, I'll get that the mass of my solute is 1.727 kilograms. Now I have some other units there that my calculator spits out, and you should just keep those around and we'll use them in the next step. I'm not going to write out every single digit because it repeats forever. All right, now I'm going to go to step 4, which is calculate the mass of solution. Well, conveniently, in this case, we actually have already done that. We know the mass of solution. And so now we're just going to go to the last step of calculate the desired concentration, which we know we want parts per million. So parts per million is equal to the mass of my solute, which is 1.727 kilograms, divided by the mass of my solution, which I know is 385,000 kilograms. So we can see here that there's not very much chlorine around compared to water and total solution. And then we're going to multiply by 10 to the 6th. Okay, when I do that, I'm going to get out 4.486. Now, how many sig figs should I have? Well, my pounds has 3 sig figs, 3.80, and my mass of solution has 3 sig figs. So here I'm going to want to round to 3 sig figs. So I'm going to want to keep these first 3 digits, and that's going to give me 4.49. And then lastly, I want to tack on my units, which is ppm. Okay, so that's how to calculate the concentration in parts per million. Hey, hey.